also know that side B is 6.4. There's a point in there, I promise. All right, so 6.4 and 12.9. And we have an angle of 13.7 degrees. Now, if you remember that formula for that page I said just a second ago, page did I say something about 84? 318. I was way off. I had an 8 in there, though. And 3 plus 1 equals 4, so... Anyway, so on page 318, there's a formula that says that if you have side angle side, you can go right ahead and say that area equals half of the two sides you know. So that would be 12.7, 12.9 times that 6.4. And that would be times the sine of 13.7 degrees. And if you just go ahead and throw all that in your calculator, you come up with your answer being 9.7. So that's 9.7. All right, so that's just one step. One quick step can get you the answer if you remember that half of the two sides times the cosine of that one. The other way you may have done it, and what most people probably did, because they probably didn't remember that, is what they said is it's half the base times the height. So I'm just going to create a height, attach it to the base with a right angle, and then all I have to do is find that h. To find that h, well, we're going to have to use sine. That's where the sine came from, that formula. So we're going to have to use the sine of that 13.7 degrees, and that's going to equal, sine is opposite over hypotenuse, so opposite is h. Our hypotenuse is 6.4. So our h is going to equal 6.4 times sine of 13.7 degrees, which should come up with h equals, I lose 1.5, yeah, 1.5. And then if you did your half your base, our base was 12.9 times the height, which is 1.5. You're still going to come out with that answer of 9.7 being your about your area. Okay, both methods are the exact same. It's just one you kind of cut out the middleman, because if you look at that 6.4, all the formula says is just go ahead and attach that in place of that 1.5. All right, that's all that's happening. That's where that formula came from. That it's one of your sides times your other side times sine of 13.7. But the big takeaway is, can you do it? Either method, don't care. All right, questions from the homework? Yeah. 53. Let's go ahead and bring that guy up. If it loads. Okay, 53. So 53 is we're supposed to determine whether each pair of vectors is parallel, perpendicular, or neither. So what do we need to do? Combine the vectors first? Well, in order to determine whether this works is we need to use that dot product theorem. For all three of those, we have to use that dot product theorem. So we have to do that cosine of theta equals our dot product on top and our magnitudes on bottom. So you need to find your magnitudes, and then you put the dot product in here. And then if this comes out to 1 or -1, it's parallel. If it comes out to 0, it's perpendicular. Otherwise, you're supposed to write neither. So either this is going to come out to 1, -1, 0, or otherwise you just say it's neither. Okay, but you have to plug it in here. Okay, that makes sense? Okay. So you may have to go back and redo those. All right, other questions? That makes more sense? Oh, good. That's why I specifically said that in class, that watch out for the one that asks for parallel and perpendicular, because that's what they're asking. No more questions? Going once, twice, 3 times a lady. Okay. So today's lesson, we're going to go into the complex numbers. And we're going to find out how we can actually graph a complex number. It sounds a lot harder than it actually is. So the first thing we're going to do is we're going to come up with our complex form, the way we've seen it every single day up until now. And that form is A plus BI. We're also going to note that A is going to be a real number. That could be like 2, 3, because we always have 3 plus like 2i, 4 plus some version of I. So that A is going to be our real. And this B is going to be our imaginary part of it. So we have a real number and an imaginary number, and that's what makes our complex number. So we have a real and we have an imaginary. Now, normally when I plot a point, I have an x value and I have a y value. I just need two values. I need something that goes on the x-axis and something that goes on the y-axis. The same thing is going to happen with complex numbers. However, now our two components are real and imaginary. So I need a real axis and I need an imaginary axis. And what we always do is we use our x-axis and we turn that into our real axis. So we're going to plot our real number on that axis. That's going to make that one that goes vertical, or y, that is going to be our imaginary axis. So we're going to turn this into our imaginary axis. And so an example of how I'm going to plot this is we're going to go ahead and plot 2 plus 4i. So we're going to note that this 2 is a real number, where this 4i is imaginary. So we go to our new real imaginary plane, and we say, well, my real number is 2, so we go to 2 on the real axis. Our imaginary is 4, so we're going to be up 4. So that means where they intersect is going to be the point 2, 4. So if I plot the complex number 2 plus 4i on this plane, it's just going to be 2, 4, which we can either write as 2, 4, or we can write it as the 2 plus 4i. Either way is correct in writing that point. All right, just one more example. We're also going to plot, I like these because sometimes these throw people. If I have negative 2i, what is my real number in negative 2i? John? It's going to be 0. And these tend to throw people. So I'm just going to rewrite this. If it throws you, I'm going to rewrite it as, hey, there's actually a 0 out there. It's just minus 2i. So that means my real is 0. So I'm going to move 0 units on the real axis. So I stay put. I am just going to go down 2 because my imaginary is negative 2. So I go down 2 and my point's right there. Okay, so we can either write this as the point 0, negative 2, which tells me that I have a 0 for my real. I got negative 2 for my imaginary. Or we can just write it as that negative 2i. Or as negative 2i. The easiest way to treat complex numbers is to pretend like they're vectors. Because we're going to use almost the exact same information that we use for vectors as we're going to use for imaginary numbers. More specifically, so vectors have A and B that we had to solve for. These are our A and our B. It's just real and imaginary. So anything we can do with A and B for vectors, we can do with imaginary and real. All right, so these are kind of like our A and B. The other reason why we want to treat these as like vectors is because we had a magnitude. We had a magnitude with vectors, right? So we're going to talk about magnitudes with imaginary numbers. However, with imaginary numbers, that magnitude that we are using for our vectors is actually going to equal our absolute value of our complex number. So anything I did with magnitudes, we are going to use to find our absolute value of our complex numbers. So for example, if I found the length of that line and I called it my magnitude, for our complex number, this is actually our absolute value. So if I find that length, this is actually my absolute. Which makes sense, because an absolute value is just your distance away from 0. Your positive distance away from 0. So if I find this distance, I actually found the absolute value of my complex number. All right, so we're going to kind of, as we do this, we're just going to keep thinking, how does this relate to vectors? And how can I use what I know about vectors in this complex plane? So let's look here. So we're supposed to find the absolute value of A and B values. Oh, and we're going to find our A, B values in the next example. So the first one, we're just going to find our absolute value. So we're going to find our absolute value of 3 plus 4i. We're going to go ahead and find our absolute value. In order to do that, we need to look at this being our absolute value. This line right here is our absolute value. That line right there is our absolute value. In order to find that, we're just going to turn that into a triangle. Just like we did with vectors, and you're going to see that everything works out the exact same. So if I turn that into a triangle, my height is 4. And my horizontal shift is 3, or my horizontal movement is 3. So that means I have a right triangle with 3, 4. And that's created by the complex number 3 plus 4i. So the absolute value, our absolute value is going to equal, well, I'm going to go ahead and call that line r, because we did that with vectors, so we're going to do the same thing with complex numbers. We're going to go ahead and call it r. Well, r squared is going to equal side squared plus side squared, so that's 4 squared plus 3 squared, which I'm just going to take the square root right off the bat. Square root of both sides means that it's going to be the square root of 4 squared plus 3 squared. Well, what that tells me is my absolute value is going to equal a squared plus b squared, take the square root. Where my a value is here, my b value is here. Well, this is the exact same thing we did with magnitudes. A magnitude equaled the square root of a squared plus b squared. So this is the exact same formula. So my r is going to equal the square root of 16 plus 9, which is 25. So that means r equals 5. In other words, my absolute value of 3 plus 4i equals 5. Another way to rewrite that is just saying the absolute value of 3 plus 4i equals 5. All right, I'm going to go ahead and write that down because that's a big thing. So our absolute value which we can rewrite as just absolute value of whatever we have, our a plus bi, is just going to equal square root of a squared plus b squared. So once again, we just treat it like it's a vector. My absolute value, which is my distance from 0, is my magnitude. Is the magnitude of that point or that vector I could attach to it. All Alright, so for the next one we don't have to draw a picture. We don't have to draw a picture, we just look at, well I did draw a picture, I put where the point was. That point is at -2, -1, so if I'm looking for my absolute value, I'm actually looking for that distance from 0. That's going to tell you that's just a vector. I just need to find the magnitude. So I just got to say, hey, my A, or my real number, is -2. My B value is going to equal a -1, which is my imaginary part. So my absolute value of 2 minus I is just going to equal the square root of -2 squared plus -1 squared, which is going to be 4 plus 1, which is the square root of 5. That is my distance to 0. Magnitude, absolute value, exact same. They're the exact same, and they're going to use the exact same formula to find them. Okay, so that's how to find our absolute value, which, like I said, is the same thing as our magnitude. So it should always be positive. All right, now we're going to find our A and B values. Pretend like we don't know our A, B values. How can we find them? Well, it creates a triangle where A is the base of my triangle, B is the side of my triangle, and we have a right angle. So that means if I wanted to find A, I could use the fact that cosine of theta is equal to a cosine, so TOA, that must be adjacent. So that would be A over hypotenuse, which is R. Multiply both sides by R, and you're going to see that A equals R times the cosine of theta. Wasn't that the exact same formula used to find the A of a vector? Yeah, that's exactly the same. What was the only difference between finding A and B when finding a vector? I changed that cosine to sine. In fact, this is the same thing that's going to happen over here. We can write it up here, but we should already know that because we're treating it like a vector, it should just be sine to cosine. Let's just check to make sure it works. Sine of theta equals opposite, which is B over R. Yes, indeedy, B still equals R times sine of theta. So if you're good on vectors, this is all the exact same information. The only difference is we're going to throw that A value in here and B value in here to see a different way to write our complex numbers. So if I replace A with R times cosine of theta and B with sine of theta, we can rewrite A plus BI in its trig form. And its trig form is going to be R times cosine of theta plus R times sine of theta. Put those in parentheses. We're going to go ahead and factor out that R in front because it's in both of them. And we're just going to rewrite this as R times the cosine of theta plus, I'm just going to move the I in front, and it's going to be I times the sine of theta. So A plus BI can be written as R times the cosine theta plus I times the sine of theta, which I also wrote down here. So this is called the trigonometric form. This is our trig form. This is our trig form. Maybe I'll mark that trig. And I'm just going to tell you this is called our rectangular form. So that's our rectangular form. That's our trig form. But both should be exactly the same. Okay, so let's use that information to solve these last few problems. I'm only going to do one of each. That should hopefully give you some time to start the homework. All right, I'm going to write this complex number in trig form. So right now I have it in rectangular form. I have A plus BI, right? Number plus a number times I. So I need to put it in trig form. That means I need to know the R value Don't forget that r is just my absolute value or my magnitude. That's just my absolute value, which is also my magnitude. And then we have to find theta, which is just the direction of our angle. So if I was doing this problem, it's always a good idea to plot that point and then draw which angle you're solving for. We're going to solve this one a little bit different than how we did vectors. This would work for vectors too, it's just a different way. Okay, so the first thing I'm going to do is, I always find my magnitude or absolute value first, because that's easy. It's just a squared plus b squared, take the square root of it. So we're going to find our absolute value first, or our r value. So our absolute value, which is my r, is just going to be r equals the square root of a squared. Well, a squared is just that first number, so that's that negative 2 square root of 3 squared, plus my b value, which is 2 squared. I want you to note real quick, have I used I in any of these? Don't throw I in there. It's just the numbers, all right? That's all we can use, because we can't do much with I unless it's squared and I can turn it to 1. But otherwise, just leave I in the forms. Don't use it. Okay, well that's going to be r is equal, let's break this into parts. 2 squared is 4. Square root of 3 squared is 3, so that's going to be 4 times 3, so that's going to be 12. Plus 2 squared is 4. R equals the square root of 16, which is 4. So I know my r value. Now I just need to get my direction. Alright, the next thing I need to do is get my theta. Up until now when we got theta, and this will work for this problem, this will be the exact same thing as what we did with vectors. You could, and let me draw it real quick, you can, and if you like doing this method, stick with it, it's a good method. You could turn this into a triangle where you know this length, and you can solve for this angle, alright, where we use tangent. Here's another way you can solve for it, is you can go ahead and say, because we're just using cosine, so I'm just going to say that, hey, I know that A has to equal the cosine, or r times the cosine of theta. I know 2 bits of that information. I know my A and I know my r. So we're going to go ahead and plug that information in. So we're going to say, well, A equals negative 2 square root of 3. And that's going to equal my r, which is 4 times cosine of theta. Divide both sides by 4, and you're going to see you have negative 2 square root of 3 divided by 4 equals my cosine of theta. Take the inverse of cosine on both sides, and you're going to see that your theta just equals cosine inverse of negative 2 square root of 3 over 4. Here's the problem with doing this method. It's going to work out this time. It's going to work out perfectly fine this time, and it's going to come out to 150 degrees. So we have theta equals 150 degrees. If you choose to use this method, make sure 150 degrees makes sense. It might actually be finding just this little section, in which you'd have to add 90 to it. It might be finding this little section, so you have to make sure it makes sense. Does 150 degrees does this look like 150 degrees-ish? Yeah. So just make sure if you use this method, it makes sense to the angle you're looking for. So now I have theta, I have r, that's all I need. I just need r and theta. So we are going to say r is 4, so we're going to have 4 times cosine of our theta, which is 150 degrees, plus I times sine of 150 degrees, and now that's in trig form. That is the trig form of it. So going from rectangular to trig, find r, find theta, just plug it in. Any questions on any one of those steps? Like I said, you can just fall back on finding this triangle, find that angle, add it to 90, and it's going to come to the same exact answer. Okay, we're going to skip this next one, and we're going to go straight down to going from trig to rectangular form. So I want to rewrite this in terms of a plus bi. In order to do that, we need to recognize that a. If you're on a test and you're not sure what you're supposed to do, write out what you know about that information. So if I wasn't sure what to do next, I'd be like, well, what does a equal? Well, a equals r times the cosine of theta, and b equals r times the sine of theta. Sometimes just writing out what everything is tells you what to do next. Do we know what our absolute value our r is? Do we know what our r is in this equation? Kelly, you're saying yes? What is it? It's square root of 2. Our r is that first number right here, so it's square root of 2. So we already know that a has to equal the square root of 2 times the cosine of theta. But theta is just our angle. So that's just going to be cosine of pi over 4. Well, that's just a number. Let's go ahead and do b. It's going to be the same thing, square root of 2, except we use sine. We still have the angle pi over 4. Let's make this as accurate as we can. So let's think back to our unit circle really quick. Who remembers what the cosine of pi over 4 is? Yeah?
Square root of 2 over 2.
Absolutely. It's square root of 2 over 2. So that means it's that second tick, right? We got one has half. Next one is square root of 2 over 2. So that means that sine is also square root of 2 over 2. So that's going to be b equals square root of 2 times square root of 2 over 2. Well, square root of 2 times square root of 2 is 2. 2 divided by 2. Hey, my a is just equal to 1. My b also equals 1. So that's going to tell me, putting it in the form a plus b I is going to equal 1 plus 1i, which is just I.